let's talk about working with images. So the simplest kind of image might be, let's say, a grayscale image. So here, let's look at even a simpler one, which would be black and white. In a black and white image, we would have height and width, and then we would just have zeros and ones. So if we wanted to have a, let's say, square in here, we could have some ones and then zeros everywhere else. So this would be a 2, 4, 6, 8 by 6 black and white image. Okay, so that's the simplest possible. If we step up from that, then we might have grayscale. So in a grayscale image, I'm going to make this smaller, we have numbers normally between 0 and 255. So let's represent this as a 4 by 4. And for each pixel, we'd have a value between 0 and 255. So normally what we would have is 0 would be white, 255 would be black, and something in the middle, like let's say 128, would be a half gray. We don't normally work with integers in this way. So here, this is grayscale, and the values are 0 equals white, and 1 equals black. Here, 0 equals white, 255 equals black, and in between we have grays. It's often very handy to work with this in some floating point number between 0 and 1. So basically, if we divide this by 255, then this becomes something where 0 stays at 0, 255 becomes 1.0, 128 becomes about 0.5, and so on. That's a nice standardization because the grayscales actually depends on how many bits you have for each pixel. So this is an 8-bit per pixel grayscale. There are certainly 4-bit per pixel grayscales or higher than 8-bit per pixel, and this provides some uniformity. So divide by the maximum value, and that will give you this range from 0 to 1. We step up from here into color images, and the most common format is RGB, red, green, and blue. There are other formats as well, like CMYK, used often for printing, or ones that are used for video. So sometimes you may have luminance and chroma and hue. I may not have those all quite right. So there are other color spaces, but let's look at the most straightforward example of RGB. So in RGB, we're going to actually take 3 different sets of values for each pixel. So again, I'm going to be looking at a 4 by 4, just a simple case. And this is the red components. So these red components, again, are going to range, let's say, from 0 to 1. So it may be in an 8-bit RGB, we're going to have 8 bits for red, 8 bits for green, and 8 bits for blue, but it's certainly easy to normalize it to a 0 to 1 range. So let's assume we've already done this. So this might be 0, 0, 1.0, 0.75, and so on. So that's the red component, and now we have a green component as well. So our green component for a particular pixel may have some other value. So for instance, let's say we have a red value of 0 and a green value of 1.0. And then finally, we have a blue. Why red, green, and blue? Well, the reason is because of the cones in our eyes, right? We have 3 different types of cones, one for reds, one for greens, and one for blues. And again, for each pixel, we have a blue component between 0 and 1. So if this one were 0 in the bottom left, then the pixel in the bottom left would be green. If this were 1, then the pixel in the bottom left would be cyan, as I remember, is what happens to the combination of green and blue, I believe is cyan. But anyway, using this, you can get any combination of colors in this RGB space. That's going to cause our cones to respond, and that will generate the appearance of a particular color. So these all get combined together, and often we would represent this as some sort of a height by width by 3 tensor. That is some sort of a three-dimensional matrix. So we could represent this as so here we would have a 4 by 4 by depth 3 tensor or matrix. And as we looked at, for instance, this 4 by 4 here, this would actually represent a pixel where we're taking a value from the red plane, a value from the green plane behind it, and a value from the blue plane behind that. So if we looked at actual values at the top left, for instance, let's say this is 0, and the green one is 0.75. Then if we look at this combination, of course, we'd have a 1.0 here, which would be in this top right cell. And then we would have a 0.75 here, and finally a 0 up here. So we would look at that slice, that cell slice through and get the values. So how will we actually feed this into a neural network? Neural networks, as we have seen so far, really have a layer of particular size. And then we have a bunch of inputs to the layer of this size, x1 to some xn, and those all feed in. Well, we can do that. Okay? We could certainly take, let's say, our grayscale image and just say, okay, x1 is going to be the first cell, x2, x3, x4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Feed in these 16 values. Admittedly, 4 by 4 is absurdly small. We're going to have larger values than that. But in any case, feed this in to a fully connected layer, right? So x1, we get multiplied basically by a matrix, M, and how big would this matrix be? So let's say this size, just for the sake of argument, is 100. Then this matrix is going to be, so our input is a 1 by 16. So our matrix is now going to be a 16 by 100 matrix, fully connected. Okay, which means that any one of these perceptrons in here, any one of the nodes in here, has input coming from all of the x's and has a corresponding weight. So that could certainly work. We might have multiple layers in our neural network, and that is one possibility. What we lose out on, though, is the structure of our original input, in the sense that the neural network knows nothing about the x1s through xn's and has no particular reason or realization that x1 is next to x2, for instance, or that x1 is a pixel the next to x5. It would have to learn all that spatial organization. And in fact, if you had one of these fully connected networks, you could go ahead and take any permutation of the x's, that is any permutation of the pixels, and as long as you were consistent in your training, then it would certainly learn just as well. So we are going to look at alternates, where we're going to try to actually deal with the fact that we know something about this spatially, right? We know that this pixel is next to these pixels and has some relationship to them. So that will be the next lecture that we're looking at. As far as color, well, we would have to, and this, by the way, is called a flattening. So we'll flatten this two-dimensional, right? So this would be a 4 by 4. And we would go ahead and flatten into a 1 by 16. We could do the same thing over here, right? We could flatten 4 by 4 by 3 into a 1 by, well, what's it going to be? 16 by 3, so a 1 by 48. And then feed it in here. It turns out it's going to be handy, though, to actually deal with inputs that actually have a structure to them. So we don't have to have just flat inputs. We can actually take structured inputs. And that's what we're going to look at shortly.